This video is for section 4-8, using factoring to solve inequalities. We just finished a section where we used factoring to solve equations using the zero product theorem. There's a blank spot here in the video, it should say 0. If the product of factors is equal to 0, that allows you to determine something about the factors. At least one of them must be 0. Let's write some related theorems to the zero product theorem. The product of an even number of negative factors is positive. For example, -3 times -5 has an even number of negatives, so the answer is positive. The product of an odd number of negative factors is negative. For example, -2 times 8 is equal to -16. There's only one negative, which is an odd amount of negatives. We can use those theorems to solve polynomial inequalities. Let's try an example. Graph the solution set of x squared plus x is greater than 6. First, subtract the 6 to get a 0 on the right side. Then factor. This can be written as x plus 3 times x minus 2. If this was an equation, we could solve by taking each factor and setting equal to 0. But this is an inequality, and it has a greater than 0. According to the first theorem on top of the screen, what can we conclude about the factors? For the product of two factors to be greater than 0, that is, to be positive, there has to be an even number of negative factors, meaning neither of these factors is negative or both of them are negative. Let's write down those possibilities. Possibility number 1, neither of them is negative. X plus 3 is greater than 0, and x minus 2 is greater than 0. If both of those factors are greater than 0, then their product would be greater than 0. Possibility number 2, both of the factors are negative. X plus 3 is less than 0, and x minus 2 is less than 0. If this is negative and this is negative, then their product would be greater than 0. Let's solve every one of these inequalities we've written. X is greater than -3, and x is greater than 2. Numbers which are greater than -3 and they are greater than 2 could be simplified to just saying x is greater than 2. Now case number 2. If you subtract 3, you get x is less than -3, and when you add 2, you get x is less than 2. Combining together what these two statements really mean, we could write x is less than -3. Remember that we could have situation number 1 or situation number 2. So our answer is that x is greater than 2 or x is less than -3. We can graph that on the number line. There's an open circle at 2 and shade the numbers greater than 2. There's an open circle at -3 and shade the numbers less than -3. Any value that's in a shaded region could be used as a solution to this inequality. Let's try another example. Graph the solution set of this inequality. It already has 0 on the right side, so let's factor. There is a GCF of a, leaving a squared minus 9. The a squared minus 9 is a difference of squares, and so it factors using the double parentheses. A plus 3 times a minus 3. We have 3 factors multiplied together, and the result is less than 0, meaning a negative number. What did that second theorem say about multiplying things together and getting a negative answer. You have to have an odd number of negative factors. So we have some different possibilities. Possibility number one, maybe the first factor is negative and the second factor is positive and the third factor is positive. If so, there would be an odd number of negative factors being multiplied together, which would create a number less than 0. Situation number two. Maybe the first factor is positive and the second factor is negative and the third factor is positive. If so, there would be an odd number of negative factors. Situation number three. Maybe the first factor is positive and the second factor is positive and the third factor is negative. And finally, situation number four. Maybe all three factors are negative. If you had a negative number times a negative number times a negative number, the answer would be less than 0. So a is less than 0, and a plus 3 is less than 0, and a minus 3 is less than 0. Let's solve every one of these inequalities that we've written. This first one, we have a is less than 0, and a is greater than negative 3, and a is greater than 3. Let's think about what this really says. The number must be less than 0, and it must be greater than 3. That's not possible. Situation number two. This one says that a is greater than 0, and solving this middle part, a is less than negative 3, and solving this last piece, a is greater than 3. Let's think about what that's really telling us about the solution. A is greater than 0, and at the same time, it's less than negative 3. That's not possible. That's an empty set. Case number 3. A is greater than 0, and a is greater than negative 3, and a is less than 3. Let's think about what all these pieces are telling us. We need a number greater than 0, and it's got to be greater than negative 3, okay, and it's got to be less than 3. Combining that together, a must be between 0 and 3. Situation number 4. A is less than 0, and a is less than negative 3, and a is less than 3. Is this an empty set, or does this actually describe numbers? This can be expressed simply as a is less than negative 3. We wanted to find numbers that worked for a, and we considered the different situations that would create an answer less than 0. We found out that 0 is less than a, which is less than 3, or that the a can be less than negative 3. Now we can graph that on the number line. Open circle at 0 and open circle at 3, and shade the numbers in between. Then an open circle at negative 3 and shade the numbers less than negative 3. Any number on a shaded region could be used as an answer for a. Let's summarize the lesson. We extended the technique about solving equations using factoring to solving inequalities using factoring. Put the polynomial on the left side, a 0 on the right side, and factor that polynomial. Then consider the possibilities of which factors might be negative and which might be positive for the inequality to work out.